So I wanted to kind of set the table a little bit with my perspective, and so you have a frame in which to understand everything I'm about to say. So what do? I'm primarily a computer scientist. So what does that mean? That means my primary output for my job is writing academic papers. It's not producing software. Caveat to that is software really matters to users, so software is important to me. I mentor a lot of students, so I'm frequently dealing with people who are learning Spack for the first time. And I'm kind of the build system / tooling people in my ecosystem and community, which means that a lot of people come and talk to me when they have random Spack problems, because I'm the one who probably, on our team at least, knows how to fix it. And then if I need to, I escalate it to the rest of the group. Research-wise, I do work on scalable data infrastructure for AI. I do work on lossy data compression, which is what I'll be talking about mostly today. And then I'll be talking about data management. So this is like kind of novel approaches for things like checkpoint restart, so on and so forth. What are my goals for the talk today? I want to provide constructive appreciation and gripes to the Spack core team and other communities about my experience with the Spack and the experience of my community. I want the audience to come away with better understandings of how we manage complex software infrastructure with Spack and some of the techniques and tricks we've used to accelerate our development processes. We hope that this will benefit the broader Spack community by shedding light on things that need maybe some additional polishing from the perspective of someone who's tried literally every Spack feature since I started using it 5 years ago. So I want to start off with a little bit of my experience with packaging, because I've been kind of the packaging tooling guy for a while. So my uncle introduced me to Fedora back in 2010. And basically, once I got into university, I switched over to Mac OS. That was a mistake. But I have since learned from my ways, and I have gone back to Linux. But during that time, I got introduced to a bunch of kind of Linux tooling and packaging techniques, things from RPMs, setup tools, Docker containers. Eventually, I was introduced to CMake as part of my coursework. And then I had this like rebellious phase in college where I thought that Arch Linux was a good idea. So I did that for a while. Eventually, I caught the HPC bug when I got introduced to using the Palmetto cluster at my university, which is at one point, it was a top 100 on the top 500 list supercomputer. I got introduced to LMOD, learned to hate LMOD, then was introduced to Gentoo and Portage. So if you have ever heard of Portage or Gentoo, it is Spack, but way harder to use. So that kind of gives you an idea. Eventually, I decided that I didn't like rebuilding LLVM and WebKit all the time, and I switched back to Fedora. And around that time, I started my grad school process where I wrote this library called libpressio. Libpressio is a library that abstracts across a collection of different scientific advanced lossy compressors. We started off with two of the major ones developed over the course of the project called ECP, called ESZ and ZFP. And then I got introduced to the ECP team. I learned about Spack through one of the ECP annual meetings. And then I kind of adopted Spack around the time that libpressio supported 12 compressors. But it gets worse, because today we have more than 50 different compressors that we have to support. And it's a complete and utter software dependency hell. So I kind of view it in some sense of my way of bringing religion to dependency hell in the course of that. So kind of talking a little bit about my experience with Spack and the impacts that it's had on me and my community. We're able to support requests for installation. So basically problems people had getting our software installed went way down, where the number of citations of people actually using our software went way up. And actually, so people actually being able to install our stuff made our academic publications easier for people to adopt. We do a tutorial every year at SC. So as part of that, we build a complex software environment that we use for the tutorial. That process went from like building the gold for that tutorial went from 7 days or more down to a single day each year. So Spack really driving a lot of productivity improvements there. It replaced a really, really ugly build script. It made ability to do source builds very simple, and it gave us a very iterative process that guaranteed that we didn't accidentally introduce circular dependencies in our build. And gave us a lot more build isolation, just made that process a lot simpler. Additionally, we've seen increased contributions to our projects from people using Spack because they're using features like Spack Develop, which makes it very easy for them to test the changes that they're making to our software and then rebuild their entire application stack on top of that. So overall, Spack has been a huge kind of lever that allows us to accelerate the science that we're aiming to do. Now, most of you have probably never done anything in software data compression before, so I'm going to give you a very brief overview on why it's important and what we do with it. So why lossy data compression for science? So modern scientific applications and instruments produce mind-numbing volumes of data. So a good example of this is LCLS2. I think Valerio talked about this yesterday. As they deploy their new system, they're expecting to have certain beamlines that generate a terabyte of data every second. That's painful. Modern cosmology simulations are expected to produce on the order of 23 petabytes of data. That's painful. So when you're thinking about it, you need to do something to decrease that pain. You need to better deal with the amount of space that it's taking up. You need to better be able to transfer data across the network, especially even wide area networks increasingly. And compression can be a big part of that story. So what we see as compression developers is we see a whole litany of different scientific applications increasingly relying on data compression to deal with the massive data challenges they have as part of that. So compression can help by reducing the data footprint, so how much space the data occupies either in memory or on disk. You may be familiar with lossless compression techniques. So this would be zip files is a great example of that. Z-standard, I think, was mentioned yesterday as a compression library that people are using. That's great, except for when you have 23 petabytes of data, because lossless compression, especially for binary floating point data, can only get you maybe 10% space savings. Well, that's nice. That's not really moving the needle. So you need to be able to move to what's called lossy data compression. So lossy data compression is more like things like JPEG. And what this allows you to do is you can make the data dramatically smaller, but then it's on you to make sure that you've correctly preserved that data. So me and my team develop a set of tools, both mathematical and software, that facilitate the process of understanding what exactly you're giving up when you're making your data substantially smaller. I work on a number of projects related to compression, funded mostly by the DOE, but also some by NSF. So FZ is a project designed to build tooling for specialized compressors. ZF is primarily a theory project aiming at developing new theory around lossy compression. And Illumin is the project I work with Valerio on, where we're looking at using compression in light sources. In each of these cases, we have a pretty complex software stack that we use. So Spack plays a role in all of these projects, even the theory ones. So this is just the run and link, or excuse me, just the link dependencies, not just the run dependencies for our software tutorial that we do each year. And there's 284 of them. In total, I think there's close to 500 packages in our tutorial environment that we use. So just giving you a kind of an impression that this is a very robust, very large, and very complex software community. It was mentioned earlier today, like how are different applications using these tools, and what roles do facilities have? What does Spack have to do with it? So we did a survey of all of the different application groups that we work with for compression, and we kind of recorded each of their requirements. And what's kind of interesting here is we asked them how do they install their software. So what you'll notice here is all of the ones I've highlighted in green say that Spack is pretty critical to how they install and use software. The other thing that's kind of interesting here is only a handful of them, namely Fusion and Climate, mention site modules as a major way that which their application scientists actually use software. In my opinion, that has some implications for how facilities should think about providing software to their users. Because users want newer software packages. They want the ability to customize them. And we expect that adoption of things like Spack will continue to improve and spread, especially for the tools like, for example, cosmology, still manually compiles a whole bunch of stuff with CMake directly. Now, I suspect that will become less and less viable as they adopt more and more complex GPU dependencies, especially things like Cocos, for example, or maybe the AMD ROCm stack. But for now, they're happy building their things from source by hand. I expect that will change, though. So what draws us to Spack? You can use it as a privileged user. It's language agnostic, distribution agnostic, great support for the software for scientific packages, expressive and easy to write DSL, generally very sane defaults. We'll talk about some exceptions to that in a second. Third-party repo support, so basically the notion of overlays, if you're familiar with the portage style of things, and an extremely supportive Slack community. I'm very thankful to Todd. I'm very thankful to Phil, to Harmon, to Massarilio, and to others, to Greg, and many others in the Spack team who have helped me with answering various questions over the year. Tamara, I believe, is another one who's helped me a lot. So I'm very, very thankful to both the core team, but also the extended Spack community. I've had great conversations with John and with, I forgot your name, but I am the worst with names, by the way. But,
I'm Lewis.
What? You're Lewis? Okay, nice to meet you, Lewis. So fast forward to today, I maintain about 50 different Spack packages. The one you've probably actually used if you're not a Lossy compression person is GDB. I support 17 institutions worldwide using our software stack. We build container images for our compression tutorial about once a year. And I've actually even contributed a tiny amount of code to Spack core dealing with a specific interaction with the build system. So now we'll move on to some Appreciate gripes. So starting off with some appreciations, compared to 5 years ago, Spack install is way, way faster, except for when ALCF disables POSIX logs, which I don't know why they do, but they do. SpackM dev file, I think Harmon was the one who originally contributed that code, is much, much faster, except for when Bazel and Ninja don't respect the, okay, the Bazel bit I'm pretty sure has not been, but the Ninja bit I think will or has been very soon to be fixed. Binary caches with some significant rough edges that I'll talk about in a second, and Ccache support is also super helpful. Spack's concretizer is way more friendly than when it was backtracking based, written in Python, so I appreciate the improved flexibility of the concretizer that has been developed over the years. Variant propagation and then the concretizer figuring out how to propagate variants for things like CUDA is substantially nicer than what it used to be. And even support for heterogeneous clusters, so the cluster I mentioned, Palmetto, I think has 18 different generations of hardware in it, which I'm seeing people kind of groan, but like universities, as someone else said earlier today, tend to have very heterogeneous hardware stacks because they get their money for their new hardware very piecemeal. So being able to do x86 architecture levels and make sure that you have something that's relatively fast and will run on 2/3 of the system is actually somewhat useful for us. Developing software on Spack has become dramatically simpler. Environments are way better, in my opinion, the best way to use Spack, much better than Spack load, substantially less error prone. Spack develop makes it trivial to develop and edit an entire mono repo full of different software packages, and I'll demonstrate a little bit of that later today. And then one of the other features that I really love is the support for Git versions, especially with the recent change that allows you to say this Git hash is equivalent to this numeric version in the spec file, which I believe Phil contributed, as Todd is gesturing. So all of these things are super, super useful and have dramatically improved the way in which we've written software. Now I'm going to get to some gripes. I know that some of these things are being worked on. I know that in some cases there are PRs for fixing them, but there are some things where there could still be some improvement. So the first gripe I have is that the concretizer doesn't filter out build cache entries that are not available on the build cache. So the most common way that this happens is you set up a build cache on some particular version, and then for whatever reason, Spack's infrastructure garbage collects the package, but leaves the index entry saying that it exists on the server. So that when Spack then goes to do its concretization, it downloads this index and then says, oh, there's this version of GCC that's available. And then it goes to download that version of GCC. It's not actually available. So then it says, oh, I need to build that. But I don't have the compiler that I need to build that because I don't have GCC 10.5. So if we could find a way that it would maybe fall back a bit more gracefully, or maybe check if the package is actually downloadable at the time where you do the concretization, would be extremely useful in filtering out those kinds of errors. 2, the concretizer occasionally makes extremely bizarre decisions. Who has heard of a package called MPI Lander? I see one hand. So the 2 people in the back of the room who have used MPI Lander, what does it do? Well, it screws up your build, that's one thing. But for those who don't know, MPI Lander is an implementation of MPI where the maximum size of MPI COM world is 1.
It's a test mock.
I understand that it's a test mock, but is that ever what you wanted if you didn't explicitly ask for it?
I'll just point out, we don't prefer it.
I know.
We somehow accidentally install it, and then we prefer it.
Yes, which is a particularly infuriating.
Which is, so Kathleen did that
Yeah.
So we're working on that one because there are too many providers and not all of them.
Yeah. Likewise, occasionally because of the weights in the concretizer, it can prefer to install an older version because installing the newer version would mean that it would have to turn off more variants, which means that occasionally it makes some weird decisions there. So at least a little bit of ability to kind of inject some additional weighting or preference there would occasionally be useful. My last kind of gripe about the concretizer is that it's extremely excited to build new LLVM. It's like, it's like, okay, a new patch release of LLVM has come out. Guys, I know what we're doing for the next 2 hours. Ideally, I would be able to tell Spack, well, I do want LLVM, but like I only need one of them. Except for if I genuinely do need a new one for my thing to work, or if I say -- fresh, then I know what's coming to me. Like I am getting ready to commit acts of self-flagellance. But like notwithstanding, perhaps in CI, as I think was discussed that we're going to do in Spack Gantry, we're going to start collecting some of this build performance data, using that to maybe influence the concretizer about how often it should try to rebuild things. Would probably be a good improvement. Another gripe, this time transitioning to topics about development, I can still, if I am feeling extremely pedantic, I can still write a faster development build script by hand than what Spack is capable of doing. It's gotten way closer than what it used to be, so now the gap is much smaller. But here are kind of the 5 things that if I were to make quick changes that I would do. So I would replace the linker with LLD instead of ld.so by default for every CMake build, which is, I think CMake provides a flag that allows you to do exactly that. And for especially things with large link libraries, think LLVM, that one change speeds up your build by like orders of minutes. Another one is Spack has like hard-coded support for Ccache, which Ccache is great. Like I'm very thankful that Ccache is there, but Mozilla wrote a better thing called sccache, and we should just use that. And I believe, I've forgotten your name one more time, but Ryan has actually written some support for that. So hopefully that particular thing will get fixed soon. The other thing that's nice about sccache is it supports CUDA and Rust, which the default Ccache does not. So you get even faster developmental builds. I don't know why we have any version of Ninja in Spack that is not Kitware's Ninja, because Kitware's Ninja actually supports the job server, which means that LLVM just doesn't crush your build. We should just set the CMake provider to Ninja by default and use the Kitware one.
Once we merge so you saw Kathleen talking.
Yep. Yeah.
Once that's merged,
yeah.
That's happened.
Okay. And talking with John, sometimes I know I'm making an ABI safe change. I would love to see kind of the libabigail stuff that he's talking about come to fruition where it would detect, oh, you didn't change the ABI of the package that you've Spack developed. Therefore, I don't need to rebuild the 50 packages that are on top of it. So that would be wonderful. John, I will be very thankful to you when that is completed. And then the last thing is dealing with testing. So I use ctest a lot to test our packages. There's not an easy way to interact with a ctest. I can like go into the build directory of a Spack developed package and I can run ctest and it will do the right thing and I can filter out the tests that I want to run. But that's like jumping down into like the depths of the plumbing in order to do something that I think is a very common use case for development. I've also run into some cases where non-hermetic builds lead to some reproducibility issues. Okay, I have a handful of minutes left, so I will accelerate. So non-hermetic builds, lib format provided by Fedora 42 has a BMI for a C++ 20 module. CMake finds that and then segfaults because you tried to build with a GCC version that was older than the one that produced the BMI. I'd like to be able to stop all downloads that happen during Spack builds so that the CMake doesn't bring anything that's not declared by Spack because it's almost always the wrong thing. And I'd like it to just not have a way to tell CMake, don't look in any directory that's not on your prefix path for anything, for any reason. Better opt-in telemetry would be very useful. There's a number of cases where binary packages are broken. A good example of this is LLVM Clang has paths that aren't relocated. that need to be fixed. Another good example of this is if you accidentally get a -m arch equals native, then you get x86 v4 symbols on your CPU on your x86 v3 binary, so that's annoying. And then for a while, Spack was using CXX11 ABI instead of the CXX14 ABI, which meant that you got all sorts of funky linker errors as a result. Occasionally, we need some additional support for relocating things that are not ELF paths. A good example of this is in GDB init. There's a file in GCC that tells it how to interpret the standard library. That path needs to get relocated in the GDB init file, and I don't think there's a mechanism in Spack to do that right now. A couple just minor packages missing. There's not a CUDA-compatible GCC in the build cache for the dev tools. You get some really inscrutable errors when a package is not available. Handful of missing dependency types. The biggest one being able to split cross-compilation things. We have some WebAssembly in our pipelines, so if you're building things for WebAssembly, Spack still doesn't detect things like fabrics, resource managers, or GPUs automatically in most cases. That would be something nice. Most common questions I get from students, why is this feature missing? Why does it take so long to install? Or why do I need to reinstall? All of these have good answers. The other question I get is what the, and that's usually because they hit some horrible problem with a broken binary package or externals polluting their build environment. So hermetic builds and binary packages that work is kind of the most important thing to me. I was going to kind of show off some different tips and tricks, but I will jump to the end because I believe I am out on time. Go ahead.
Great. Let's thank Robert. Maybe we have time for one question as the next speaker sets up.